Welcome, everyone, and thank you for joining us today. My name is Paul Donahue, and I will be your host. We ask that you please keep your device muted during the session, and if you have questions, please direct them to me using the chat function. We'll do our best to answer questions at the end and follow up with unanswered questions by email. As I think you know, these Tech Talks have been designed to provide straightforward insights into radio frequency components, related technologies, and the extra design and engineering value that is added by custom manufacturers such as Quantic TRM and Quantic Corry. To begin today's session, I am pleased to introduce Eric Zacherl, Senior Engineer at Quantic Corry. In addition to being on the team for several years, where he focuses on PCB design and switch matrices, Eric is a musician and a private school educator in the electrical engineering area. This diverse set of skills enables him to bring some unique perspectives and analytics to his work. So welcome, Eric. Can you share an overview of today's topic and your objectives for the session?
Hi, Paul. Thanks. Yes, today we're going to talk about radio frequency switch matrices. What are they? We're going to talk about the different architectures that are available for them and some of the relevant electrical specifications that really define the switch matrix itself, and a little bit about control interfaces available, and we'll talk about an example application as well.
Excellent. So to get started, can you define a radio frequency switch matrix? It's hard for me to say it, a radio frequency switch matrix.
Yeah, sure. It's hard for me to say too. A radio frequency switch matrix connects one or more input signals to one or more output signals. It's really that simple. So as you can see in the little picture in the slide there, lots of connector inputs and outputs. And that's what we'll be dealing with today.
Okay. And are there different types of switch matrices?
Yeah. So there are three main types or three main architectures. The blocking is a very popular one. It allows you to route one signal on the input side to one signal on the output side. Each input can connect to one and only one output. So that's why it's referred to as a blocking matrix, because if you take input one and select output two, it blocks you from being able to select one of the other outputs as for a different input.
Okay. So if one type of switch matrix is blocking, should we assume then that there are also unblocking matrices?
Well, that's a good lead-in. Thank you. Yes, there are non-blocking type matrices, and following the diagram there, you can see this one is a fan-in type non-blocking matrix, because on the left-hand side, what you can see are 4-to-1 splitters on those inputs, and they can then be routed to the outputs. So the splitters allow you to route one input to more than one output. So it's said differently, each input can simultaneously connect to multiple outputs.
Okay, so are there any additional types that you'd want to talk about?
Yes, so there is the super non-blocking. The super non-blocking is very similar to the non-blocking, except as you can see in the little diagram there are splitters on both the input and output ports. And, that gives you a great amount of flexibility, because you can combine signals in many ways. This is also known as a full fan-out matrix, because you could, for instance, connect input one to all four outputs, or some mixture of inputs to some mixture of outputs. It's really quite flexible, and those connections can be done simultaneously.
Well, could you maybe give us some insights then into some of the electrical specifications associated with these?
So the electrical specifications that are important for a radio frequency switch matrix are operating frequency. So, do you need this, what carrier frequency do you need your switch matrix to operate over? And the insertion loss, very important. Can the customer in the application tolerate a great amount of insertion loss, say 10 dB of insertion loss, or is the signal coming in pretty sensitive, pretty small, and any attenuation on it would affect the measurement level? Then having a much lower insertion loss would be of greater advantage there. Then the return loss, how well matched is your device under test or test equipment? How well matched is that to your switch matrix? And isolation is another important specification, because you may not desire to have crosstalk between inputs or outputs. And so particularly in a non-blocking matrix where you don't have those splitters in there, the isolation tends to become a very important spec, although it's also important in the non-blocking matrices as well. Then going down the list, the noise figure. So particularly when we're dealing with small signal sources, low noise amplifiers, things of that nature, the noise figure comes into the picture just to prevent the noise floor from affecting the accuracy of your measurements. And then the switching speed. So how fast are you going to need to be able to switch the configuration of your switch matrix from, switching input 1 between output 1 and output 2? How fast does that need to happen? And then the power capability, also very important. If you're trying to switch a transmitter to multiple antennas, you might need a much higher power handling capability than if you were trying to connect a receive antenna to a receiver, something along that nature. And then whether the switch matrix is unidirectional or bidirectional, i.e. can the signal flow from the input to the output only, or from the output to the input as well? So can the signal flow both ways, which is obviously bidirectional. The characteristic impedance, usually 50 or 75 ohms, and our linearity specification. Do you distort the signal at higher power levels? At what power level does the signal start to distort? That would be a measurement of linearity. And another one would be phase matching. Some applications, such as Butler matrices or hybrid couplers, have a phase accuracy that is associated with them that you might want to hook up to your matrix and test. And those things would require a switch matrix that has phase coherence.
Wow, well, that's quite a number of specifications. How do all of these impact technology decisions then?
So really all of those specs drive the technology that is chosen to construct the matrix out of. What building blocks, what ingredients does that switch matrix need to contain in order to satisfy all the customer requirements, i.e. electrical specifications. So we have a number of technologies that will fit the bill, if you will. We've got solid state switching, or what we call FET-based, MOSFET-based switching. So we've got relays, mechanical relays, electromechanical relays, excuse me, and pin diode switches. So, and you would choose one over the other for various reasons. Solid state switch tends to be quite fast in switching speed. Just as fast as a pin diode switch, but there are pros and cons to having both of those. A pin diode switch is much more expensive than a solid state switch, for instance. If you need to have a really high power switch, and the speed is not as important to you, a relay switching type matrix would be more to your benefit. And then we've got a couple other ingredients that we mix in there as well. You can amplify the signal through the switch matrix, and this would help your insertion loss. In those instances where the lowest insertion loss is required, then having amplifier in the switch path is of benefit. But the drawback there is then it makes the switch matrix unidirectional. So the RF signal will only be able to flow in the path of amplification. It won't be able to pass back through from the output of the amplifier to the input of the amplifier. So it's a double-edged sword. And then the user customer can specify what types of coaxial connectors they want. SMA, N-type. Those are two popular coaxial connectors, and characteristic impedance of 50 or 75 ohms. And as I mentioned earlier, phase matching. And phase matching does come at a price premium, and that's because at gigahertz levels, things of that nature, a very small physical length difference can really affect the degree of phase matching. So it becomes very challenging to do a phase matched switch matrix properly. But we're capable of doing such things.
Okay. Now, earlier you had mentioned that switch matrices connect input signals to one or more output signals, but can you tell us a little bit about how they interface?
Yes, I can do that for you. So, we've talked about the RF interface, the inputs, outputs, the switches, how it gets there. This is the control interface. So, how does the user select which switching paths that they want to use? Which input do they want to connect to which output? Or which inputs do they want to connect to a single output if it's a non-blocking matrix, vice versa, if it's a super non-blocking matrix. So some of the remote interfaces that are common and popular are Ethernet, USB, GPIB, serial buses, straight digital I/O, where you would just toggle a pin electrically, put a high or low, 0 or 5 volts, or you can have no remote interface. If you have no remote interface, then you'd be required to have a local interface. Otherwise, the switch matrix would be kind of useless. Some of those local interfaces, depending on what the use case is and customer requirements, could include a touch screen. touchscreen displays, very popular nowadays. And then something that's a little less sophisticated, but still widely used are display with tactile switches. And when I say tactile switches, I mean, like a number pad or something like that, where you can, feel a little feedback going click on there. Or just a simple toggle switch. You want to switch one input on or off. It's just like flipping a light switch. You turn it on, you turn it off. And if you've got a remote interface, then a local interface isn't absolutely required. Not all switch matrices have a local interface. So you can have a remote interface and a local interface, or you could have just a remote interface or a local interface. They're not mutually exclusive.
Okay, well, maybe you share an example.
Okay, so the example that I'm going to present here is a 4 input by 4 output non-blocking switch matrix. And so for this, we came up with some requirements, frequency range of 1 meg to 18 gig, 100 microsecond switching speed max, 20 dBm power input, 100 milliwatts, insertion loss less than 3 dB, and you can see the rest there. And the slide shows a picture kind of what a switch matrix like this with N-type connectors would look like.
So which technologies then would be required in this case?
So for this case, solid-state switches would probably be your best bet. The reason that is you need the fast switching speed. Mechanical relays cannot switch that quickly. Pin diode switches can, but they come at a price premium. And in this particular application, they're not required because the power input is low enough that a solid-state FET-based switch will do the job here and do it well. Other thing you might note on the diagram here is, we have the splitters on the left-hand side, and this would be a fan-in non-blocking switch matrix. If you imagine in your mind's eye flipping that, mirroring that, this could be a fan-out type switch matrix as well. We've chosen to focus on these slides on the fan-in type. Those are all the pictures that you've seen thus far. But just be aware that fan-out is also an option, something that I meant to point out earlier. But then also for this particular example, amplification is required. And why is that? That's because those input splitters have a theoretical loss of 6 dB, and it will be slightly more than that, due to non-idealities. So our insertion loss requirement from our specs was less than 3 dB insertion loss. And so we need to put some amplifiers in here. And in this diagram, those little triangles are representing those amplifiers. So you can see they come directly after the splitter, and in that way, there's minimal loss in front of those amplifiers. And so you'll get a better noise figure, better return loss. All those electrical specifications would be optimized in that case. And then, on the output, we've got our single pole 4 throw switches.
Wow.
And yeah, so a lot there.
I was going to say that's a lot of good information. Maybe you could summarize.
Our RF switch matrices, their applications are for switching one or more outputs to one or more inputs. and they really save the user from having to move connections from one device under test to a bunch of test equipment, and really can make your test setup or your system, your switching system, be more user-friendly and less wear and tear on your RF connectors and cables. And then we have the three different architectures, the non-blocking, blocking, and super non-blocking. I mentioned those in different order than they were presented in the slides, but those are the three types. And really, the electrical parameters, electrical specifications that the switch matrix must satisfy, those are what's going to determine what's inside the box, the customer requirements. And that's why it's not a one-size-fits-all sort of device. The switch matrices are often very customized for the customer application. And going along with that, not all customers have the same user interface needs. So being able to select those different ingredients is very important as well.
Okay. And, I suppose just like as you've said, not all customers have the same needs across the board. Not all custom manufacturers are the same either. How would you describe some of the Corry differentiators? What's different about the way Corry operates, Quantic Corry?
So what we do here is we interface with the customer directly. The engineers will talk to the customers in conjunction with sales, and we will get to the optimum solution that fits the application. And sometimes it takes a little bit of discussion to get to that point, but we pride ourselves on being customer friendly and meeting the needs. That is our calling card, if you will. We do industrial, aerospace, medical, military, and we are here to provide solutions. Our goal is customer satisfaction and to create unique solutions that make our customers successful in whatever systems they're trying to press into use in the field.
Okay, excellent. Thank you for that. And I think we have time for one question. And the one that came in, when would it be appropriate, Eric, to use non-blocking versus blocking type matrix?
So, as I alluded to earlier, there are two non-blocking types of matrices. The super non-blocking and the normal non-blocking. And the use case where you take a non-blocking as opposed to a blocking would be if you need to combine signals. Say you want to route one signal to various pieces of equipment, then a non-blocking matrix is what would be necessary in that case. And if you, on the flip side of the coin, if you only need to connect a single port to a single output port, a single input port to a single output port, then a blocking matrix is what is required.
Okay, well, terrific. So in conclusion, I think that everything on the screen more or less speaks for itself. And I think that if you are a customer and you have additional questions, or if you'd like to discuss an application with our engineers, We would love to hear from you, and you can please feel free to call the engineering hotline. The number is on your screen, 724-940-7556, extension 276. And of course, there's no cost associated with these calls. And going forward, our next Tech Talk will be on Tuesday, October 24th at 1 p.m. Eastern. And the topic will be what we're calling Space 2.0. So thank you again for joining us. And Eric, thank you.
Thank you, Paul.